Hello, and welcome to Senior Code Review Buddy. My name is Chris, and today I'm going to walk through a coding interview problem. I'll talk about how to come up with a solution, and then how to code up that solution. Over the years, I've probably done around 200 technical interviews, evenly split between in-person and phone screens. I'll go over one of my favorite questions to ask. It's called the museum guard problem. Basically, we got a museum, which is a nice grid shape with locked and unlocked rooms. Then there are some guards placed throughout the museum in the unlocked rooms. What we want to know is, for every room, how many rooms away is the closest guard? Locked rooms are inaccessible, so they'll get a value of infinity. For unlocked rooms, guards can visit any unlocked neighboring room, up, down, left, or right. No diagonal moves. Now, I've also included a link to a write-up of this problem in the description below. Alright, so let's start thinking about how we'd solve this problem. For the complete solution, we want to find the closest guard for every room, but what if we started by solving a smaller chunk of the problem first? This might feel less overwhelming to start with, so let's start by finding the closest guard to a given room. So how can we approach this subproblem? Well, we could start by going over the grid, finding every guard, and then use a pathfinding algorithm like Dijkstra's to find the shortest path between each guard and our room, and then we just return the minimum value. While this sounds like it could work, this also sounds pretty expensive. Having to compute the shortest path from the room to every guard doesn't sound ideal. In theory, if we do each guard one at a time, we'd be able to stop searching for any guard if their path is going to be longer than the shortest path we've seen so far. While this would probably make the code run quite a bit faster, it doesn't change the big O performance, since the guards could be arranged in a way that this doesn't help. But that is a hint. Could we maybe just perform one pathfinding run to find the closest guard? Could we just evenly search out from our room and find the closest guard? Let's think about what that might look like. So, starting from our initial room, there are 3 states it could be. The room could be open, locked, or have a guard in it. If the room is locked or already has a guard in it, we know the answer right away. The locked room can't be reached, so the value is infinity. And if the room has a guard in it, the value is 0, since the guard is in that room. So that's 2/3 of our cases already handled. So how do we handle the case of our initial room just being an open room? Well, since there's no guard in the room, we know that either the room isn't reachable, or the closest guard is at least 1 room away. So how do we check to see if there is a guard 1 room away? Easy. We just check all the neighboring rooms. So we check the 4 neighbors, and if any of them are guards, then we know the value is 1, and we're done. And if all the neighbors are locked rooms, we also know this room is unreachable, and we're done. But what happens if neither of these conditions are true? Our neighbors are just some more open rooms. Well, just like before, we now know that either no guard can reach our room, or the closest guard is at least 2 rooms away now. So we'll now want to visit the unvisited neighbors of these rooms, and I can see a pattern here, and it sounds like a breadth-first search. If we use a breadth-first search, we know that when we reach a room, all rooms that were closer to our initial room have already been examined. So the first time we see a guard, that guard must be the closest guard to our room. There could be a tie, but there couldn't be another guard closer. And if we complete our search without finding a guard, it means no guard can reach our room. If you've not heard of breadth-first search before, or just need a refresher on how exactly it works, I've added a link to the Wikipedia page in the description below. When I'm interviewing people, I'm less interested in generally if someone immediately sees that this is breadth-first search, and more interested if they can sort of describe the pattern and sort of see how they would use this approach to help them solve the problem. Now, is this an optimal solution? If our museum is a grid of m by n, our breadth-first search performance for big O would be m times n. And in order to have a better search performance than that, we wouldn't be able to examine every room. And I don't think we can find a solution that is guaranteed to be correct if we don't visit every room. So we've got an optimal solution if we are solving for just 1 room. We can use this approach to solve for the whole museum, but our performance there gets a lot worse. Since, as I just mentioned, there are m times n rooms in the museum, our performance is now m times n times m times n, or m squared times n squared, which feels pretty bad. So is there a change we can make in our approach to get a better runtime when solving for all rooms? The first thought that comes to mind is we are running so many breadth-first searches on the same grid, but we aren't sharing any information between them. Each run is starting from scratch, but they have so much in common. Thinking back to our one-room solution, instead of doing pathfinding for every guard, we just did one breadth-first search that included all the guards. So maybe we can do something like that here. What if instead of finding the closest guard for each room, we got the distances from each guard to every room? So instead of starting our breadth-first search from every unlocked room or every room, we just start from every guard. This feels like it would be a nice improvement, as there's probably going to be a lot less guards than unlocked rooms in the museum. And while this is probably true in a real example, it's not guaranteed. In theory, every unlocked room could have a guard in it, so our big O performance is going to stay the same. We are on the right track though. We just need to make one small adjustment. What if instead of starting each breadth-first search from scratch, we used the same grid? That's to say, we complete the breadth-first search for our first guard, and then moving on to the second guard, we use the same grid. So instead of visiting every room that the second guard hasn't visited yet, we only visit rooms where the second guard is closer than the first guard would have been. Because if they were further away, we're not going to see any improvements from that room or anything down that line. So we don't need to evaluate it. So now we are sharing information in between these runs. But unfortunately, like before, this doesn't change our big O cost yet, since depending on the order the guards are processed in, we can't promise that this will be a more effective route. But there does seem to be potential here. So what if instead of running the searches one at a time, we did them all at once? We could run a breadth-first search, and instead of having one guard as the starting point, we could make every guard a starting point. We can easily adjust the code to do that. And at this point, we are just running a single breadth-first search, which seems pretty good. So we are now going to scan the grid once to find every guard, which is big O of m times n, and then performing one breadth-first search, also big O of m times n, which gives us an overall solution of big O m times n. And I don't think we can improve on that, since once again, that would require not visiting every room, which doesn't seem like it'll work. So, alright, I think we've got an optimal solution. Let's move over to the coding side. So I've got a little code here to start with. We've got our initial function, find closest guard to each room, which takes in the museum width, the museum height, and the museum grid itself. And then we'll start by initializing an array for closest guard to be the same size as the museum grid, and we'll initialize each room to be -1. So we'll start with assuming that no room can be reached by any guard. Then I've added a small test case class underneath it with a basic test. So we'll just do a 3x3 museum with a guard in the middle and open rooms. This just gives us a way to see how our approach does. So we start and we run, and it doesn't work, which is expected. So let's start writing our solution now. So let's start by having the list of nodes or rooms that we want to visit. So we'll have to visit. And then what we're going to do is we'll start by finding every guard, because as I mentioned, that's what we want to start with. Range, width, if, museum, okay, so we go, we add the guards with their starting position, and we also include a value of 0, which represents the distance that we are from a guard. It's important to remember that we need to make sure we treat toVisit as a queue, because we want to make sure that the first rooms we add are the first rooms we visit, first in, first out. Otherwise, we might not be following the breadth-first search rules, and we could visit a room that isn't technically the closest unvisited room yet. Now that we've got our starting points, we'll just iterate over them. So while we have something to visit for an X, for an Y, distance. And remember, we need to make sure that we pop off the first room to make sure that we're doing it in first in, first out. So now we actually check, we check the closest guard value to see if we have visited this position or not. Because if we have visited it already, which would be indicated by having a non-1 value, there's nothing to do. In this case, another guard already got here. We're not going to find the shortest path, because we know that's how breadth first search works, so we don't have to do anything. So we only need to continue if we haven't already visited this position. And if that's the case, then also for the same reason, we know that we are the closest guard, so we can set that value to our distance. And now we'll need to add neighbors. And a nice way to do it is to add sort of a loop of how all the neighbors can be accessed. Because this way, we can sort of loop over this to find each neighbor, instead of having to have 4 different hard-coded cases. So we now do for delta y, delta x in neighbors x equals corrects. So we will add on every neighbor that is within the bounds of the museum. So they can't be a negative number, and they can't be too high for the museum. Oops. And we also need to make sure that they are not a locked room. So if all of those conditions are true, what we want to do is add this new one to our toVisit queue. We give it the new x, the new y, we give it distance, +1. And that should be it, so let's run it now and see if the test passes. Oops, I didn't mean push, I meant append. There we go. The test is passing, so I think we've got a working solution, but we do just have one basic test case. So I've come up with a couple of other test cases. Let's take a look at them and see if things are working good. As I mentioned, we still have our basic test. Now, some of the other tests that I thought about. So I try to think about edge cases and other things that might cause my code not to work the way I expected or to be something weird. So one example, obviously, is there's only guards. Everything should be a 0. All right. There's another one. No guards. Everything should be -1 then. Unreachable. What if it's only locked rooms? So no guards, but again, all unreachable still. All right. What if the museum isn't a square? All of my previous examples so far have been a square. Let's try one where it's not. Just make sure I didn't flip numbers around at any points. What happens if the guards can't get to half of the museum? So in this situation, I've got a line of locked rooms through the middle of the museum, 1 guard on the right, and nothing on the left. So these are unlocked rooms, but no guard should be able to reach them. And then I sort of added just a little bit of a bigger museum, kind of following what seems more like expected data. It's not really an extreme one way or the other, it's just kind of a mix of things. So if we run this all now, excellent, we see that all of the tests pass. So I think that means we've got sort of all of the main cases that I can think about. We've got this one just big museum case that we've run, so I think we've done pretty good, and I think we can consider this problem done. And if you are interested, there's a link in the description below that goes to a copy of this final code I had here, so you can copy it, play around with it, and look at it if you want. I hope that you found it interesting to walk through this coding interview problem with me. This is pretty different from the other content I've been thinking of making for this channel, So please leave a comment below letting me know if you want to see more stuff like this or less. And if any parts of this were confusing or you think I skimmed over something interesting, please let me know in the comments below and I could address it in a future video. If you enjoyed this video, please consider hitting the like button below and subscribing. If you have any other comments, code you'd like me to review, or ideas about what you'd like me to talk about, please leave a comment below or reach me at chris@seniorcodereviewbuddy.com. Thanks, and have a great day.